Hi, you're watching Pikai Pharmacy. So today in this video we're going to learn about potentiometric titration. So before starting the video, a quick context that in this video we are going to discuss about the theoretical concept that how we can use a potentiometer to determine the endpoint of a titration. So let's begin. So let's discuss about potentiometric titration. So potentiometric titration is a volumetric method in which the potential between two electrodes is measured. That is, one is reference electrode and another one is indicator electrode. So the potential difference between these two electrodes is measured as a function of their added reagent volume. So now from this equation you can see that the total cell potential is equal to the potential of the indicator electrode, which has a potential that varies with the concentration of the analyte. That means the potential of the indicator electrode is not constant, minus the potential of the reference electrode. So the reference electrode has a known potential that remains constant with constant temperature. So that means we know the potential of our reference electrode, which is constant, plus the potential of the junction electrode. So I need to talk a little bit about this. So we know that in a potentiometric cell there occurs a salt bridge that prevents the component of the analyte solution from mixing those with of reference electrode. So a potential develops across the liquid junction at each end of the salt bridge. So this potential is called junction potential, which develops across this salt bridge, and it is so small that we can neglect it during the calculation. So now you can understand that in potentiometric titration it is nothing but here we obtain the endpoint using the change in potential during the titration. So here you can see two graphical representation of the potentiometric titration. So the first graph is the electrode potential versus the volume of titrant added, and in the second graph it is nothing but the data of the first graph plotted in y-axis versus the volume of titrant added in the x-axis. So from both this graph we can understand that as we keep on adding the titrant, there is not that much change in potential, but when we approach towards the endpoint there occurs a huge change in the cell potential. So this quick change in the cell potential denotes our endpoint. So the volume corresponding to that change in potential denotes our endpoint. So at that point we should stop adding the titrant. So in the endpoint we observe a huge change in the cell potential by this potentiometric titration, and we can determine our endpoint. At first we are going to apply this potentiometry in our acid-base titration. So here our acid is HCl and the base is NaOH. So we will use the sodium hydroxide as our titrant and the HCl will be our analyte. So as we have done in our past, like we have added the phenolphthalein which changes its colors at the endpoint from colorless to a pale pink color. So here we will not do like that. So here we will apply the potentiometry, that is we will observe a change in the potential in the potentiometric device. So as we know that during titration the HCl reacts with NaOH to form its respective salt, that is NaCl. So when all the HCl gets used up to form this NaCl, that point is our endpoint. In this acid-base titration, our reference electrode will be a saturated calomel electrode and the indicator electrode will be a glass membrane electrode. So as we know the mother formula, that is the E potential is equal to E indicator minus the E reference, we are not including the junction potential as it is very small. So the E potential comes out to be E indicator minus E reference. Now we know that the indicator potential is equal to standard indicator potential minus 0.0591 log of the hydrogen ion concentration. So we can put that value in the place of this indicator potential, and minus 0.2422 This is the potential of our reference electrode, that is the potential of saturated calomel electrode, which is constant, that is 0.2422. So now let's concentrate on the fact that during this acid-base titration, the H plus ions released by HCl gets used up to form this H2O. So the number of H plus ion decreases as we proceed towards the endpoint. So as the concentration of the H plus ion decreases, so we can see the log of the hydrogen ion concentration also decreases. So when all the hydrogen ions released by this HCl gets used up to form this H2O, then this hydrogen ion concentration will be 0. Then the log of 0 will turn out to be 0, which will cancel out this total component, and there will be an increase in the total cell potential. You can see if this goes out, then there will be a increase in the total cell potential. So why this is going out? Because all of our hydrogen ions released by the HCl gets converted to H2O at the end point. So the log of 0 hydrogen ion concentration will cancel out this total substance from our equation, and we will get an increase in the cell potential. So you can see an increase in the cell potential in the potentiometer during the titration, and that indicates our endpoint of the acid-base titration. So in redox titration, we will apply the potentiometry. So as you know that in redox titration, both oxidation and reduction takes place. So here our oxidizing agent is dichromate ion, which oxidizes all the Fe2 plus ions in our sample solution to Fe3 plus. So when all the Fe2 plus gets converted to Fe3 plus ion, we will obtain our endpoint, which means when all the Fe2 plus will get oxidized by this dichromate ion to the Fe3 plus, then we will obtain our endpoint of the titration. So here in this potentiometric titration, we are using saturated calomel electrode as our reference electrode and the platinum wire as our indicator electrode. Again, we know our mother formula, that is the cell potential is equal to indicated potential minus the potential of our reference electrode. Again, we know that the indicator electrode potential is equal to standard indicator electrode potential plus 0.0591 divided by n multiplied by log of Fe3 plus ion concentration over Fe2 plus ion concentration, where the n denotes the number of electron transferred during this oxidation reduction reaction. So again, in the place of indicator electrode, we will replace its total value minus the potential of our reference electrode, that is 0.2422. So now this is our final equation for the total cell potential in case of redox titration. So in this above reaction, the number of electrons transferred is 1. So we will replace the value of n with 1. Now again concentrate on the fact that as we approach the endpoint, the concentration of the Fe3 plus ion increases. So as the concentration of this Fe3 plus ion increases, there is an increase in this total log value. So as the total log value increases, it gets multiplied with this value, and this whole thing adds up with the total cell potential. So there is an increase in the total cell potential as the concentration of the Fe3 plus ion increases. So this increased Fe3 plus ion concentration at the end point increases this log value to a very high amount, which adds up with this total cell potential and causes increase in the total cell potential. So at the end point, there will be a huge change in the total cell potential, and we can see it by the reading of the potentiometer, and at that point we should stop our titration. And we can also apply this potentiometry in precipitation titration. So here is an example of precipitation titration where the AgCl forms the precipitate at the end point. So at the end point the metal ion concentration increases, which increases the log value and adds up with the total cell potential. So there is an increase in the total cell potential at the end point. So you can observe a sudden increase in the total cell potential if you look at the potentiometer, and that indicates your endpoint of the precipitation titration. So now you know the theoretical concept of how to determine the endpoint of a titration using a potentiometer. And I would also like to tell you that we can use this potentiometer to determine the endpoint of complexometric titration also. So I hope you like this video. Thanks for watching. Stay healthy. Bye.